Okay, welcome to lecture 3 for Stat 479. So today we're going to build on what we covered in the previous lecture. In particular, we're going to look at multivariate linear regression in a little bit more depth. So in particular, we're going to focus on analysis of the least squared estimate, and we're going to introduce some concepts which relate to how we're going to analyze these estimates based on bias, variance, and mean squared error. Okay, so recall the general framework, and this is something that I'm pretty much going to put up at the beginning of most lectures because it's going to be our kind of reference frame to see, to be able to compare different methods and look at the particular scenario that we're in. So remember that the first component is the data, then there's the statistical data generating model, then there's the estimator or algorithms, and there may be more than one, and then there's the analysis. So we started to talk about multivariate linear regression in the previous lecture. And so we covered, I'd say, the first three components of that, which were the data, the model, and the estimator. So the data here is we have p variables x and then a response variable y. And we're able to very conveniently write this in matrix form. So x is an n by p matrix, where n is the number of samples and p is the number of covariates or features. And we have an n-dimensional vector, so one for each sample. And so the model that we consider is the linear model because we're doing linear regression. So typically you want your method to match your model. And so the model we consider here is the standard linear model. So in matrix vector form, you can write this as y equals xb plus epsilon, where b is like your parameter coefficients. It's a p-dimensional vector. Epsilon is an n-dimensional noise vector. And so far the assumptions we're making on epsilon is it has mean 0. We'll later look at other assumptions that we're going to put on that later on. And this will be relevant in our analysis. And the next thing that we consider is the estimator or the algorithm. And so what we use there is the least squares estimator. So we have that b hat is some element or some solution to the least squares problem. I've used this notation epsilon here or this notation element of here because there's certainly scenarios where this is not unique, particularly if x is rank degenerate. So if x does not have rank p, then this is certainly a non-unique solution. And so we'll later make assumptions to make this unique when needed, but in general, this does not have to be unique. And we can see that by taking derivatives and setting to 0, we get what was called the normal equations from the previous lecture, and any solution satisfies these normal equations. So it's x transpose x beta hat equals x transpose y, and so that's that holds for any solution. And so we're going to use the two things to keep in mind that we're going to use a lot today are this linear model y equals xb plus epsilon, and then these normal equations x transpose xb hat equals x transpose y, because these are properties of the original model and then the estimator. So today we focus on 4, which is the analysis component. And so what we mean by analysis typically will be like, what can we say about b hat, which is the estimator, compared to b, which is the true parameter of interest in our model? And so this is where we use the linear model and those normal equations that we know about b that y equals xb plus epsilon, where epsilon is some noise. And what do we know about b hat? And we know that b hat has to satisfy the normal equations. And so the key question that we're going to look at today is how close is b hat to b? So to address that question, we need some some performance or closeness metrics to determine how close is b hat to b. And there's going to be three that I'll list here, and I'll talk a little bit about each one. So I'll state them first, and then we can... And so this is referred to as mean squared error. The MSE. And what's important to note here is we have an expectation here because B hat depends on Y, which is random. So expectation is taken over epsilon. You can think about that, or Y, because remember that Y is a random variable that depends on epsilon. So that's why we have an expectation here, because B hat's going to be random. And this is a pretty widely used metric. The second one, we'll see that it's going to have quite different properties, but it's also related, and it's got this X matrix here. So this is referred to as mean squared prediction error. And so we'll use the acronym MSPE. Once again, the expectation's taken over the noise epsilon. We have this 1 over n factor out the front because we're going to normalize because we have n samples, and we're really looking at kind of like a sample by sample error because we multiply by this matrix X, so that's an n by p matrix. So that's why we have this 1 over n factor. And the other, so what we're really measuring is what we're really measuring here is how close is x beta hat to xb, or xb hat to xb. So this is why it's referred to as prediction, because it's possible that b hat and b won't be very close, but xb hat and xb will be very close. And we're going to see examples of that either maybe later today or in other lectures. And so that's why it's referred to as mean squared prediction error. Third one, which we'll spend the least amount of time on, but it's still worth mentioning. It's very related to the second, but there's a little bit of difference that we'll talk about. This is referred to as out of sample. So we'll say this is OSPE. So one thing to note is and so the important thing, and this is actually the most widely used metric in practice, and the reason for that is in practical applications, you actually don't know what the parameter is. That's what you're trying to infer from data. So throughout this course, when you'll be doing some simulation studies where you'll know what that B is, that B, like that true parameter B. But in most practical applications, you don't actually know what that is. So that's why you can't actually compute either metric 1 or 2 like in practical settings. So what people typically do is that they just look at Y, like, how close is Y to X beta. So we're measuring Y to X beta hat. And so that's something that can be that can be computed more easily. So this, and we'll see that this is this is going to be quite related to that second metric, MSPE. Okay, so the other thing to mention here is that the definitions that I wrote, I introduced today's lecture. We talked about the estimating procedure being the least squares estimator, but you could certainly use other estimators. So we'll later discuss the maximum likelihood, and you could potentially use any other estimating procedure you like. And those three performance metrics, those B hats can be any of those performance metrics. And these three performance metrics are great because you can actually compare different methods. So if you were doing maximum likelihood or least squares or method of moments or any other procedure that you can think of, you can see which one, how these methods compare in terms of any one or all three of those performance metrics. Later today, we're going to focus on the mean on how these three metrics look when we're talking about the least squares estimator. But you should keep in mind that these metrics hold for everything. So you should keep these metrics in mind as a tool for comparing different procedures. Okay, and so the next statement that I say is going to apply to any estimator, so not just least squares. So we're going to specialize this discussion to least squares later, but what I'm going to say next applies to any estimator, whether it be least squares or maximum likelihood. So what I'm going to do now is talk about the fact that the mean squared error, both 1 and 2, so the mean squared error and the mean squared prediction error, they actually decompose quite nicely into two sort of pretty intuitive quantities, which are known as the bias and variance. So let's define this. Okay, so we're first going to define these notions of bias and variance. So firstly, the bias for an estimator is just how close is the expectation of b hat to b. So we know that, let me just write this out a little bit more neatly. So we know that b hat is a random variable. You know, it depends on our data, x and y, whereas b is a true parameter. So one natural question to ask is, in expectation, is how close is b hat to b? And so if we can further say that if, you know, the bias is 0 or equivalently E of b hat equals b, then b hat is what's called unbiased. And you might view unbiasedness as generally a good property. We'll see that it is good sometimes, but actually it's not always that good, and we'll see sort of why throughout the course. We'll see that the least squared estimator often is unbiased, but there are other estimators that are not, that are actually very good. And the reason why it's not is because of this next quantity, which is the variance. Okay, and so this really goes back to this really goes back to your notion of variance that you would have learnt in probability before, which is that the variance of a random variable is really just the expectation of that random variable minus its expectation squared. And so this is really just saying like how much variability is in b hat. Okay, and note that there's no b in this definition, so this is purely something that's saying how much noise or how much randomness is in this b hat. And so this leads to the bias variance the bias variance decomposition for 1, which is the mean squared error. So we can say that the mean squared error, b hat, is just okay, so this is the bias variance decomposition that we see. So the mean squared error of b hat is going to be the squared bias of b hat, so the bias squared, plus the variance of b hat. So if we view the mean squared error as a performance metric, we want low bias and low variance ideally to give us good performance. Okay, so now let's let's talk through this a bit. So And so, as I mentioned, to get a low MSE, you need low bias and low variance. And so, you want to find estimates that do that. But what we'll actually see later is there's often a trade-off between these two quantities. So sometimes you can find an estimate that has very low bias but very large variance, and as opposed to other estimates that have very high bias but very low variance. And we're going to see examples of that both later today and throughout this course. But, this is one thing to keep in mind when thinking about analyzing estimates, like this bias variance trade-off, like how much bias is there and how much variance is there. This is something that's pretty straightforward to prove, so I'm going to go through that. You can, in math, you can always kind of add and subtract things together, and that's exactly what we're going to do here. Okay. And then we can just expand out the squares, which seems like a reasonable thing to do here. So we're going to get okay, so we get these two terms. And then in addition to that, though, we always, like whenever we expand squares, we get a cross term, which is something we have to think about. Okay, so what I've done here is essentially just used some basic properties of expanding out the squares in vector form, which allows us to expand that out. And so what we can see here is that we get that this is the variant. The first term corresponds exactly to the variance of b hat. The second term corresponds exactly to the bias squared in vector and from the notion of vectors. So when I say squared here, we can imagine the norm of that vector squared, and then we get this extra term here. And so what we kind of would want to show is that this extra term here is 0. So this is a vector b hat minus e of b transpose, b hat transpose, and then okay, and so just also to be clear, the reason this is the bias is because e of b hat is a constant and b is a constant, so that expectation here, you can just drop it because the expectation of a constant, as we know, is just a constant. And so if we look at this term specifically, this is equal to 2 times, if we bring the expectation inside, we just get okay, and so this thing is 0, and so we get what we what we kind of wanted to see, which was that this is just the variance of beta hat plus the bias squared of b hat. Okay, and so this proves the bias variance trade-off, and it's just some simple algebra. Okay. And then the other thing to note is that So we have a similar result for 2. So MSE of x b hat equals the bias squared of x b hat plus the variance of x b hat. And I'm going to leave the proof as an exercise because it more or less follows identical steps. So that's something that I encourage you to try to do on your own, because that'll give you a sense of how these calculations work, and you'll be doing these kinds of calculations on the first homework. Okay, so everything that I've spoken about in the last 15-20 minutes, there hasn't been anything specific about least squares. So now we're going to return our discussion to least squares. So the next question is, for the least squares estimate. So remember that we have that for a least squares estimate, we know that that satisfies this this equation, or any least squares estimate satisfies this equation, these normal equations. And then we also know that the model we have is that y equals xb plus epsilon. For the rest of today's lecture, we're going to assume that rank x equals p, or x transpose x invertible. And what this means is that is unique. So there's exactly one least square solution. So this is something that we're going to assume. We'll talk throughout the course that this doesn't always have to be true, particularly in high dimensional settings where the number of variables p is large. But for the discussion today, we're going to assume that, and then we're going to branch out a little bit later. So for now, we have a single, a single simple least square solution to analyze. So we have that b hat equals x transpose x inverse x transpose y. And then we also have that, so we know that and then we know that y equals xb plus epsilon. So what we can actually do, and this is something that's very commonly done in statistics, and it's a very useful analysis tool, is that you can just plug that in. You can just plug these equations in now. So we have that this is the expression we get, and so this very conveniently works out to be. So this calculation is only possible because of the fact that we have the invertibility of x transpose x. So now what we can see quite clearly is we can actually address the question of bias straight away, because we have that okay. And then this is just b plus, the only randomness here is in the noise, and because expectation is a linear operator, we can just take it inside. We know that this expectation here is 0 because it's a noise by definition. So we have that the expectation of b hat equals b. So therefore b hat is unbiased. Okay, and so we can therefore say that the MSE of B hat is just purely equal to the variance of B hat because the bias is 0. And so what we have then is that the MSE of B hat is equal to the variance of B hat, which is equal to the variance of or we can kind of write this out as because this is because epsilon's mean 0, we can just write it out like this. Okay, so next what we're going to do is we're going to use some matrix tools here. So we can express this as the expectation of the trace of the of this matrix. So this is a standard kind of trick, I guess, from linear algebra. Okay, so this is a general expression. We've made no assumptions about the noise other than the fact that it's mean 0. And so it looks a little bit complicated, but we'll see that that's going to look a lot simpler once we make some nice simplifying assumptions. So what we can do is we can make the assumption that the expectation of epsilon transpose is sigma squared I, which is the identity matrix. So epsilon transpose is an n by n matrix, and we're taking the expectation of that, which just is the entry-wise expectation. And so we're assuming this is the identity matrix times sigma squared, which this is very standard. And so this is so the noise epsilon is independent, so and homoscedastic. This is a K, sorry. So that the same variance. You'll get a homework exercise where this is varied a little bit, where we'll have independence but not homoscedasticity. But this is an assumption that will make the calculations pretty nice, and it's also a very standard assumption in practice. So we have that. Okay, and so because expectation and trace are both linear operators, we can take that expectation inside, and all of these x's are just constants. So I'm doing a lot of using linearity and properties of linear algebra here, and because this is sigma squared times the identity, we get something that works out really nicely here. And so this gives you that we get sigma squared, the two of the inverses cancel out, and we get trace of X transpose X inverse. So recall that trace is the sum of the eigenvalues of X transpose X. And so And this quantity is related to how correlated or dependent covariates are. And if that statement doesn't make sense to you yet, that's okay. We'll see evidence of this later. But what we can see here is that our final expression is that we have that it's sigma squared, which is the variance of each noise variable, times the trace of X transpose X inverse. And one thing to note related to, I talked about bias and variance. So we have that for B hat, which is the OLS estimate, so ordinary least squares estimate, or we'll just be consistent here. We'll say the least squares estimate. Note that bias is 0, so we're unbiased, and variance and this could be potentially large. Can we think of an estimate? Can we think of an estimate with large bias and small variance? And at first hand, it may not be obvious, but it turns out that I can give you a very simple one, which is that what if I just told you that B hat was 0? It sounds like a pretty dumb estimate, but it turns out that it's got what's the variance of B hat? Equals 0, and then the bias of B hat equals to the expectation of B hat minus B, which is just obviously just going to be negative B, right? Because the expectation of B has 0. So what we can say then is it's actually not a bad estimate if B is very close to 0. But obviously, in general, this is we'd have to be relying on the fact that B is close to 0 for this to be a good estimate. And so this actually has a much lower variance, obviously, than the least squares estimate, but it potentially has a really large bias. Okay, and it also turns out that that least squares estimate is the unbiased estimate lowest means lowest MSE. If we assume So if we assume that I'll just write this out again as well. If we assume that E of epsilon 0 and that we have these this sort of homoscedastic noise that I spoke about. Sorry. If you assume that you have this homoscedastic noise that I spoke about, that amongst all unbiased estimates, the least squares estimator has the lowest mean squared error. So it's often referred to as blue. So often it's said that LS is blue, and what that means is it's just the best linear unbiased estimate. Is unbiased estimate with lowest, and if we also assume things are linear, and we'll actually see. So that's a good property of least squares, but we're in about weeks, maybe 4, 5, 6. We're actually going to see estimates that are biased, and in many settings, these might actually do quite a bit better than the least squares estimate. But amongst unbiased estimates, the least squares estimate is the one with the lowest variance or the lowest mean squared error. Now let's look at the second metric. So this is metric number 2 that I illustrated above there. And so we're looking at this again for the least squares estimate. The expectation of 1 over n x b hat minus b squared. And so once again, we know that, so we do similar analysis to what we did before. So I'll go through it a little bit more quickly this time. So we have that and once again, if we invert the expression, so we're assuming invertibility here. So we're kind of assuming that X transpose X matrix is invertible. Then what we get is that okay, so we once again get something pretty similar, but we get this X out the front. And we'll see that that's actually very significant and important, that X, because that'll mean that we get lots and lots of nice properties of this this expression that actually makes the calculation look pretty nice. And so also note that the bias is 0 again. So this is just equal to the variance. So Okay, so now let's look at this in a little bit more detail. So let's so look at this matrix X transpose X inverse X transpose. One thing that's nice about this is that it's an orthogonal projection. So what that means is that if we let, let's just say, I'm using this notation pi x because pi sort of, it's what's used in math for projection. We can see that pi x squared is equal to pi x. So if you square it, you get back exactly the same thing because the inverses cancel out. And the other thing that we get that makes it orthogonal, so that makes it a projection. What makes it orthogonal is that if you take the transpose, then you also stay the same. So what that means is that if we look at then we once again can rewrite this as the trace of this pi x epsilon epsilon transpose pi x transpose. Okay, and then once again, so the calculations are pretty similar to the original MSE. We can bring the expectation inside. So we're again here going to use the so this, like everything I've done here, makes no further assumptions about the noise other than mean zero. But now we're going to again assume we're going to assume that this covariance is just sigma squared times I, so we get sigma squared over n. And so now what is so we can also further simplify because we have those nice properties of this orthogonal projection. This is just equal to sigma squared over n times the trace of pi x. Okay, because pi x transpose equals to just pi x, so then you end up with pi x squared, which is just pi x. And then what's the trace of a projection? So this just ends up being it ends up just being so for orthogonal projections, all eigenvalues are either 0 or 1. So that's kind of what that basically means, is that the trace here is just going to be the rank, because you're just going to count all the non-zero eigenvalues, because if you sum up numbers that are either 0 or 1, you just have to count the number of ones, and that corresponds exactly to the rank. And so what's the rank? you can actually just show that that just equals to the rank of x. And so you just get this very nice expression that's sigma squared over p on n. And that's a very, it's a very nice expression. It's basically saying that p is just the number of parameters, n is the number of samples, and sigma squares is the noise variance. And so one thing to note is no dependence here on matrix X, which is pretty cool. It only depends on the sample size n, the number of parameters p, and the noise variance sigma squared. So the MPSE that we get is sigma squared p over n. And so, like I mentioned, for the b hat, we noticed that there was a term there that depended on the correlation amongst the features, because like we had an X transpose X in there. So recall MSE of we had that this is a trace of X transpose X inverse. And we can clearly see that we don't have like that, and that's something that clearly depends on X and depends on the correlation of the features. We don't have anything like that here for the MSPE. And so that's really nice. So finally, in the last few minutes, we're just going to talk about the so the third metric here, which is the out of sample prediction error. Okay, so we have again that so this is just following on from the previous calculation. I've skipped a few steps from before because I've already done this calculation. And we also have that y equals xb plus epsilon. So we can see that so we can clearly see that the xb's cancel out, and you end up with and so this is equal to, and we can once again we're going to again use this notation in terms of a projection, because that'll make things sort of nice and allow us to use to exploit some nice properties of projections. And what you can say once again is that the identity minus pi x is also and so what we end up with here is, again, something that where the calculations end up being pretty nice. So we're going to get a sigma squared over n once we take the expectation inside, times So we're again going to use properties of orthogonal projections here. And once again, every projection, orthogonal projection, the eigenvalues are 0 or 1. So this is just going to be the rank. Okay, and what you can sort of see is that this is just going to be sigma squared over n, and then the rank of that is just going to be the rank of I minus the rank of this pi x. So you're just going to get n minus p. So we're going to get this very nice expression of okay. So that'll be more or less it. So just we're going to summarize things here. There's quite a lot of math and quite a lot of new concepts in today's lecture. If it feels like it's a lot, that's okay. We'll hopefully start to become more familiar with this as the course goes along. Part of this was just to sort of lay some of the foundations that we're going to build on. So terms like bias and variance are very useful terms to talk about estimates and compare different procedures. And then we also got to see sort of how we can use some linear algebra techniques to analyze the least squares estimator. So summary, we defined these three metrics: MSE, MSPE, and OSPE. And for the first two metrics, we can actually show a bias variance decomposition. Nothing like that holds for the third metric. And we're going to, so in the next lecture, we're going to kind of round off this discussion and then talk a little bit more about sort of algorithms, so procedures to actually find that least squares estimate. Okay, thanks very much, and have a good rest of your week.